Greetings once again, everybody, and welcome to Trigonometry for Students and Surveyors. We're now doing lesson 10. So just to recap our first few lessons, first one was introduction of materials that you would need, computer or calculator, graph paper, scale, protractor. Wouldn't be bad to get a compass that draws circles. Then we went into right triangles. We solved those for first 4 or 5 lessons, and then we went into oblique triangles and learned about the law of sines, the law of cosines, and solving oblique triangles. All that is very practical, practical trigonometry. Now we're going to start going into coordinate geometry, and so we've got two different graphs here set up, two different graphics set up for you. Get ready to go on that. This over here is sort of a representation of typical Cartesian coordinate system, or rectangular coordinate system. This is how you've probably seen them set up. And then this is going to be something we'll get into in a minute. So we'll deal with this one first. René Descartes was a French philosopher, mathematician back in 1700s, I think, came up with this coordinate system. So let's just go through that a little bit. I don't want to spend too much time on this, and you'll see why in a minute. But we'll say that this is the x-axis. These are the x-axis. This is the y-axis. And if you were to draw, say, a diagonal line, this is going to be our point of center. That's where those two intersect. And that's 0, 0. So we're going to call that 0. We'll call that 0 over 0. So anything in this quadrant here, this quadrant here, and by the way, they call these quadrants a little different than what we're going to call ours. They call these quadrants Roman numeral 1. I'll just put it right in here. 1, 2, 3, and 4. That's how they do it, and they tend to angle, vertical angles up. So if we had our 3, 4, 5 triangle superimposed on this, we'd have it 4, 3, and then diagonal would be 5. So we could actually draw that in here. What we want to do is we want to go to 4. Let's see, 1, 2, 3, and 4. I think we want to go right here. Oh, that would be it. So this would be our 3, 4, 5 triangle. So you have, so in other words, you have your hypotenuse, wherever that hypotenuse comes from, or terminates, it's going to terminate at the intersection of grid lines going north, south, east, west, or up, down, left, right, positive, positive, negative, negative. And that's how you convert. I talked about the calculator, the polar rectangular feature in the calculator. So for instance, you could put 3, enter 4, then hit the polar rectangular, and it's going to give you this angle. If you recall, it was somewhere around 33, 38 degrees, and then it'll give you this distance at 5. If you put this angle in and then the hypotenuse, it's going to give you 3 and 4. That's the polar rectangular feature in these calculators. Very handy to have. Essentially what you're doing here is, where this is very similar to that, is these are positive. This quadrant over here is positive northing, or positive and positive. And over here you've got positive east, and so you got a negative and a positive. See, we're going to call that, well, over here we call them northern and east, and this here they just call them, they're just grids. So this is a positive and a negative. It's a negative northing, it's a positive easting. Over here we have a negative and a negative. Anything south of the line is a negative vertical. I'm getting confused because in surveying we call them northerns and eastings. I don't want to get to that yet, but I guess I might have to. I don't know. It's also latitude and longitude, northern and easting, latitude, longitude, north-south grid lines. Anyways, that quadrant is negative and negative, and this quadrant is north and west. So anything north is going to be positive, and then it's a negative easting on that. So that's how you can draw a line, put a line here. If you wanted to do there, you would have a negative 3 and a negative 3. So you'd have a negative 3, 3. You'd have a negative 3, negative 3. And that would be your coordinate for right here. So if you were to draw one of diagonals to here, you would have a positive, your northern would be 1, 2, 3, oops, 3, and you would have a negative 3 over a negative 1. That would be that coordinate right there. So you can negative 1 column. I think you know how to do that. So down here, let's just draw an arbitrary line down to, this is your hypotenuse. You'd have a positive 2 on the easting and a negative 4. That's what the coordinate system is. That's the rectangular coordinate system is. It's converting polar measurements to rectangle or rectangle to polar measurements. That's what happens when you inverse, and we'll get into that later. So that's the typical way to do it, and they usually start out with 0 here and 90 up here. That's called a vertical angle. That's why when we turn this up here, that's going to be a 38. Let me run that calculation for you. This is a 3, 4 triangle, so we're going to go 3, enter, 4, divide, or 3 divided by 4. That's 75%, 0.75. We want the arc tangent of that is 3686. We're just going to round that off to 37 degrees. 37 degrees is this angle here. So keep that in mind. That's how you do that. So we're going to find that side over there. Well, we'll just go through that. Let me just go ahead and store this as 3686.99. I'll just go ahead and store that as A. All right, we got that. Now we want to find out the hypotenuse. We want to find out the vertical on this. So we will recall that number, and we're going to hit sine, and we're going to remember our side over here is 5 because it's the 3, 4, 5 triangle. We'll multiply it times 5, and that gives us 3. Now, this is back to our 3, 4, 5 triangle, and this is what we did over and over again. So we found that by sine, and we used that angle and found 3. We're finding the opposite. So now we're pretty much used to that. That's what we've been teaching all along. Now we're going to probably get away from that and show you the alternative on that. And that will be, that's going to be fun. I'm not trying to trick you. It's just the way it is. So I'm going to get rid of all this. Well, do I have to get rid of it? I'll leave it for now. Okay. In surveying and in mapping, it's a little different. So here we have 0, we have 90, we'd have 270, and back and 360 if you were going counterclockwise. In surveying and in map reading, you go clockwise. The big difference is 0 is the zenith. It's at the top. Zenith. Zenith means top. Nadir means down. Nadir. So it's 0. Now, 0, 90, 180, 270, 360. And it also has quadrants, just like the Cartesian system does. Now let's see. There's also, so that's the azimuth. So when you go to 0, 90, 180, 270, 360, those are azimuth degrees. It also has bearings. Bearings are a little different. So the bearings, the first quadrant is exactly the same. We'll call this the northeast quadrant. That's exactly the same. Everything here is the same. It's 90 degrees. When you get to your second quadrant in bearing, you're back to 0. So you're going 0 to 90 and then back to 0. And then the azimuth, you're going 0 to 90 to 180 to 270. Here you're going 0 to 90 to 0, back to 90, and then back to 0 again. And so what that happens is you have a bearing. Let's say this is 45 degrees northeast. Let's try a different pencil here. When you have a bearing, you're going to have the exact same bearing here. 45 degrees, 45. South, west, north, east. 45 degrees northeast and 45 degrees southwest are the same 180 degree line. So in civil plans, what have we got any out here? Somewhere here there's civil plans. I do have a set here. Everything on your plat maps, your civil engineering maps, your boundary maps, your property boundaries, they're all in bearings. They're all broken down into bearings. Same with here, southeast. Any line, any 180 degree line in one direction is going to be the same in the other direction. So, and just to show you, I have two compasses here. These are compasses we use for surveying. This is a bearing compass. These are very good kind of compass. This is a Silva. This is Silva Sun 2 and Silva. Very similar, very good compasses. Sight down. So this goes 0 to 90, back to 0 to 90, back to 0. And of course it's got its declination set in there. This is an azimuth compass. And we'll spin that up there. 0, 90, 180, 270, 360. So these are your two different compasses. So I would probably recommend getting an azimuth compass because we're going to do most of our math in azimuth, not bearings. And also this is a navigation compass. This is what you use for your topographic maps if you're hiking. If you look at any Garmin, even your phone compass, everything's in azimuth, not bearing, not the quadrant bearing. So keep that in mind if you're going to buy a compass. I like these two brands, Silva and Sun 2. I believe this is a Silva Ranger Sun 2, but you can dial in. You want to? We'll do compasses later. All right. But anyway, there you go. There's that. Now we're going to do. So on this one, what are we doing here? This one is very similar to this one. We're going to get into coordinates, coordinate geometry is what they call it in surveying. That's where we're going to do the same thing as that, only we're going to put coordinates here, which is kind of what we did here roughly, very crudely, coordinates. Now, so what do we want? Get rid of this for now. This part is the same. So this is called in surveying, we call this northerings and eastings. In the global scale, it would be called latitude and longitude. Global coordinates, latitude and longitude, they basically emanate from the center of the earth, and much more complicated math to do those. This is like grid plane geometry is what we're looking at here. And we are going to do X, Y. This does X, Y. We're going to do, when you're surveying, you're doing X, Y, Z coordinates. So the Z is the elevation. So everything we do is X, Y. Everything we do is X, Y, Z coordinates. So northings and eastings. And I think they call it that because everything north is positive, everything east is a positive, south is negative, and west is negative. So over here you're going to have a positive and a positive. Over here you're going east, so that's positive, but your northing, and the northings are always on top. And I'll show you that in a minute too. And over here your northing is a negative, and your easting is a positive. So we're going east. And over here your southwest, your northing is a negative, and your easting is a negative, and northwest, your northing is a positive, and your easting I always crowd myself, and your easting is a negative. There you go. So as you go around your azimuths, you'll see all that. So now, the reason that is, so now wait, let's superimpose a 3, 4, 5 triangle on this one now. Let's just do that. We'll pretend we have one right here. We'll just do it like this. We're not, these dimensions are obviously not perfect. Those are supposed to, vertex of the angle is supposed to be right there, but that's all right, you get the idea. So we have our 3, 4, 5 triangle. So if you use this system here, and now you want to figure out 3, I'll show you here again. We're going to do that again. 3, enter, 4, divide, 0.75. We want the arc tangent on that. 36, 86, 99. We'll go ahead and write that in here. Okay, that's the decimal degrees. Anything wrong with that? So all that's right. Everything we done before was right. This is the right angle. This is that angle. The thing is though, it's not that bearing, because there's 45 right there. If you come down, this is 45 degrees. And if that's 0, and that's 45, and that's 90, then 36, 89 should be greater than 45. So why isn't it? And then well, it's because it's the difference between the sine and the cosine. The sine and the cosine are 90 degrees apart. And since all these angles that we figured out here going from vertical angle from 0 up, we're now going 0 down to 90, and everything's right angle. So there's going to be a 90 degree difference on everything we do. So 2 ways to do that. So we go 90, enter, that's our 90 degrees. And then 36.8699 minus 531301. So that's the difference. So that's actually turns out to be this angle here. That also happens to turn out to be the real bearing here. And why is that? Well, because we're coming down from the top. And I don't have my scale on here, but that's what that would be 53 degrees from there. So what we have is a sine. The sine runs like this. Starts at 0, goes up to 90, back to 180, back to 270, and then back to 0. And the cosine starts here at 0, 90, 180, 270, and then back to 0. That's a cosine, that's a sine. So they're 90 degrees apart. So what's going on here? Okay, now I remember what I was going to say. So I was using this and figuring out these triangles just like you guys have been doing. If you're following this program, following these lessons, you kind of got that down. You can do your right angle triangles. 6 ways to Sunday. Now you get to here. Now I'm getting this angle. So with my instrument here, we're measuring an angle, and it's 5313.01. So I'm used to using sine, right? Sine, 5313.01. Well, it's not going to work. It's not going to work. Why? Because now we're going to use the cosine. Well, how does that work? How is that possibly to work? Let me just show you here. So 3686.99. I think I stored that. Let's go recall. Yeah, there it is. So now if I hit sine and I hit 5, oh yeah, that's because I'm using this number here. But I'm measuring this angle now. So I'm getting 5313.01, 53. Now I'm going to hit sine on that, and I get 8, and that gives me 4. That's down here. That's not giving me that vertical distance. So, of course, I was mastering my triangles, and I get my trying it out in the field, and I get my zenith. I'm reading my zenith angles, and I'm using sine just like I was here. And I'm not getting the right answer, and I'm going, what's going on? Well, this is what's going on. It's the sine and the cosine are 90 degrees off. All these triangles we're figuring out from the normal reference of state plane coordinates. We're now using zenith coordinates, zenith generated coordinates. So what's really going on here is, let me try this one. Why is it cosine now? So cosine gives you the answer. Well, remember it's rectangular coordinate system. Here's the other half of that rectangle right there. There's the other half of that rectangle. And now, let's go. This is 4, 3. Now this is 4. This is 3. Now we'll go 4, 3. 4, enter, 3, divide, 1.33. And then we want to times 5 times. Wait a minute. 4, enter, 3, divide, 1.33. Now, sorry, well, now we want the arc tangent of that is 5313.01, and I'm going to store that as B. 5313.01. Sorry, that's a decimal. 5313.01, same as here. And of course it's going to be. So that's also going to be 36. So now if I'm trying to figure out what my height is, if I'm turning a zenith angle, and now that also is actually 5313.01 is actually the horizontal, that's the true bearing, that's the true azimuth of that circle of north. We do everything north, south, east, west bearing. We're not just doing this. This is CAD. This is for just basic triangles and for stuff. Here's what happens in the office. They'll bring in architectural plans and they use their CAD drawings or CAD drafting papers or CAD drafting, computer assisted drafting, and they'll maybe create something in CAD. All the dimensions are right, all the angles are right, everything's right, but it's in this CAD system, and we'll import it. Either the office will fix it or we will have to fix it. But in our data collectors, we have a setting that puts in, you can select northing over easting or easting over northing. And there's the odd time where that setting's been messed with somehow, where they come in backwards, and you bring in your coordinates and you look at your screen to find out where you're at, and nothing makes any sense. You don't know where you're at. You can't follow the map. It shows all the points on the ground. You keep going the wrong way, and that's what it is. So everything has to be converted for us to the true northing and easting. So that's where we're at with this now. So 5301. So now we can get the right height, which was 3. So now I want to look at an elevation. I'm looking at my zenith angle. Now when I'm talking about zenith angle, I'm talking about vertical, but then this is also the bearing horizontal. So you're always looking at, when you're looking at x, y, z coordinates, you're looking at x, y, and vertical z coordinates. So I'm referring to this back and forth. So anyway, so that's what's going on, is you use cosine where you would use sine, and then you use sine where you use cosine. If you're trying to find the distance on that, you just recall, let's go to recall b, we'll go to sine, and then we'll go 5 times, and that gives us 4. So before sine, we were solving for 3. We would use cosine. Now we're using cosine to solve, actually, this 3 here. And that's the difference in a rectangular coordinate system. So we'll get into that a lot later when we start doing our coordinates. But that's basically why there's confusion. And I've seen a lot of these trigonometry and stuff courses where they don't really get in and explain that, but that's what's going on there. They're 90 degrees apart. Cosine, this one here is sine, this here is cosine. Wave, cosine wave. And so you got to go, when you're getting stuff from your office that's back and forth, that's CAD or northing and eastings. Think of northing and eastings also like latitude and longitude on your Garmin's or on your phones, even your telephones, your smartphones have all that in there too. So okay, that's a good start on that. Now we're going to go to this northing and easting, because we're going to start doing coordinate geometry next one. We're just kind of roughing into it. So we're going to go northing is plus, easting is that. So just to, let's see, what else we want to do. To convert back and forth, let's go to that first. To convert back and forth between azimuth and bearing, that's another thing we're going to do, because I inadvertently talk bearing when I mean azimuth, sometimes azimuth when I mean bearing. But I'll try to keep that straight. So let's just go with, in this quadrant, the northeast quadrant, they're the same. Bearing and azimuth are the same. They're just written a little different. Let me, so let's just say this would be 10 degrees up here. This would be, in bearing, it would be north 10 east, and I think in azimuth it would just be north east 10. I don't think it really matters how you write it. So let's go down here to 90. So now 90 is going down to 0. Let's go to, let's go 90, 100, let's go to 110. 110. So that would be 110 on your azimuth. If you wanted to know that was on bearing, you subtract from 180. So this quadrant over here, your negative is, your northing is easting, and your Your northing is negative, your easting is positive. So we have 110 on the azimuth, that's just 110. If you want to convert it to bearing, you subtract from 180. So if that was bearing, it would be 90, 80, 70. So you subtract 70 from 180, and you'd have 110. So that's how you do that. So that's positive, negative. Over here, so on this one you subtract, subtract 180 to get bearing. And if you got bearing, then you add 180. No, you subtract 2. Well, let me back that up. All right. Let me just erase that. Over here, and over here you would add, if you have, say, 0, and then you're up here to 10, you would add 180 to that. So you'd have 190 all the way up there. Over 360, so on anything below the southern hemisphere, you either add 180 or subtract 180. It's easy to figure out. Then over here, when you're in the northwest quadrant, you use 360. You subtract 360 or add to get to 360. You don't mess with 270, you don't mess with 90. Everything, this quadrant's the same, you don't need any changes. This quadrant all goes from 180 both directions. Either add or subtract. You just gotta stop and figure it out. Maybe I'll do a little more better diagram later on. Yeah, I probably should have wrote that. So we've got that. That's how you convert back and forth. What I want to do here now, we're in the northeast quadrant, so let's just go with well, let's see what happens if I put 45. 45. Okay. All right, we're just going to do these even quadrants, just for the fun of it. We're going to go 45. I'm going to go 235 or 135. This is going to be 225. And this one's 315. So these are your northeast. These are split them 45, 45, 45, 45, 45. 45 degrees, the next one, you add 100 and subtract from the 10th. The next one, you add another 100th, subtract another 10th for 225. And over here, you add another 100th, subtract another 10th for 315. So we're going to go around and show you what happens when you hit your sine and your cosine. Because a 45-degree angle is going to be the same, just like it is on this thing here. Remember, I told you before, if you do the square root of 2 is 1.414. So all these are all going to be the same distances this way and that way to there. So we're going to go 45, that's our first angle. Now hit cosine, and you're going to see the 0.7071. So now hit 45 and hit sine, and it's going to be exactly the same. And by the way, they're both positive. So I'm going to go northing and then cosine. Then easting is sine. So have to keep this in mind. The northings are cosine all the way around, and eastings are sine. It's all going to hold the same. Okay, now we're going to go down here. Our azimuth is 135. 135. Now we're going to hit cosine. Is a negative 7071. and we're going to hit 135, and our sine is going to be a positive. So I'm going to go cosine and sine. Okay, so let's just do that one more time. 135 sine 7071. That's because we're going east. East is a positive. Everything east, northing and east. And then we're going to go 135 and cosine. And that's a negative. And that's how you'll be entering in your coordinates into your polar measurements. You'll enter them as negatives or positive, whatever it comes up to. Now let's go to the southwest quadrant, and we'll go in 225. That splits them in the difference. And we'll hit cosine, negative 0.7071, 225, and we'll hit sine, negative 7071. So we'll just make sure I put this in here, cosine, sine. So, and then now we're going to go up here to our northwest quadrant. 315 is our azimuth, and we're going to hit cosine. That's a 0.701, so that's a positive cosine. And then we're going to go back to 315 and hit sine, and that's a negative. So that kind of gets us started on what's going on with our angles. So here, so we got that. Now what we're going to do is start doing some coordinates. Unlike here where it's 0, 0, we'll usually have wherever this point happens to be. Well, we're going to get into that when I start doing traverse. But this is always thinking about your graph paper, that any place where that you're referencing from, whether you drew a line here, you have a new northing, that's again north-south. If you go over here, you have a new north. Always think of it that way. Now this is an angle and that's an angle. This is what a traverse is. You trav up to the northwest, then you backsight that. You turn an angle to this one, you backsight that, and you turn an angle. And that's what we're going to be doing. We're going to start adding these angles. But think of your graph paper as very similar to lines of latitude and longitude. And then also keep your angles are all going to be matching your graph paper grids, because that's what we do, is we're converting this polar measurement to northing and easting. So this is 5 feet, 5 feet or 500 feet on this angle, 531301, and that's converting to 300 feet up to 400 feet over. And that's the start of that project. This is the Cartesian system, but this is it with 0. Okay, let's go over this one more time. So if you're going from 90, 80, 70, just subtract it from 180 to get your azimuth. And if you have your azimuth, subtract it from 180. And over here you add 180 to get your bearing, or to get your azimuth. If you have an azimuth, if you say you have 190 here, you subtract from 180 and you'll get your bearing. So that'd be 10 degrees, 0, 10. So anyway, so the main thing in this quadrant, when you're converting from azimuth to bearing, they're the same. There's nothing to convert. It's just you might write them different. On this one, you're using 180 as your reference point. So just think about whether you're adding azimuth or you're subtracting to get bearing. And over here, or subtracting. Same with this one. You're using 180. What you're not using is 90 or 270. You're not using 90. Those don't come into it when you're calculating, when you're figuring out converting from azimuth to bearing. So you're only using, that quadrant's the same. These two quadrants reference 180, and this quadrant references 360. Okay? I think that'll just about do that for today. Kind of colorful. All right. And now we'll start carrying coordinates. We'll start doing what's called latitude and departure tomorrow. We're on our next lesson. We'll start doing latitude department. And then I'll make this a little clearer. I know I stumbled and fumbled around here. I tend to do that, but okay. Maybe a little bit low on presentation, but I think the product is pretty good. I think we're getting some good knowledge here. All right. Please like and subscribe. Please send this around to everybody you can think of. There's quite a lack of survey knowledge and trigonometry knowledge, and it's a very practical knowledge. So